Hey everyone! Tonight, we're venturing into the profound silence that follows stellar death. Before we settle in together, take a moment to like this if these cosmic explorations bring you peace, and share in the comments where you're listening from and what time it is in your corner of the world. I'm always moved by how our global community comes together to contemplate the vast universe around us. Now get comfortable, dim those lights, and let your breathing slow. Tonight, we're not exploring dramatic cosmic explosions or stellar births. Instead, we're going to examine something far more meditative and profound: the trillion-year cooling of white dwarf stars, the gentle transition from stellar fire to eternal silence. Let's begin our peaceful journey into deep time. Imagine, if you will, the final moments of a star like our Sun. After billions of years of nuclear fusion, the stellar fires that have burned so steadily finally begin to fade. The star gently sheds its outer layers into space, leaving behind only its hot, compressed core, a white dwarf star. This is where our story truly begins, not with the dramatic end of stellar life, but with the beginning of an impossibly long and peaceful journey toward cosmic silence. Tonight, we'll explore these stellar remnants that represent the ultimate fate of 97% of all stars in our galaxy. We'll discover how these Earth-sized objects, compressed to incredible densities, slowly cool over timescales that dwarf human comprehension. We will examine the gentle physics of their cooling, the crystalline hearts that form within them, and their role as cosmic timepieces marking the passage of deep time itself. These white dwarfs are not merely stellar corpses. They are ancient libraries preserving the history of stellar evolution and galactic formation. They are cosmic meditation objects, inviting us to contemplate timescales so vast that they challenge our understanding of permanence and change. In their slow cooling, we find a profound peace, a reminder that even in the cosmos, all things eventually find rest. As we journey through trillion-year timescales tonight, let these cooling, stellar remnants guide you into your own peaceful rest, their gentle transition from light to darkness, mirroring your own journey into sleep. In the vast cathedral of space, where silence reigns supreme across distances that dwarf human comprehension, there exists a profound moment of transition that unfolds with the patience of geological time itself. It is the moment when a star, having burned through billions of years of nuclear fire, finally exhales its last breath of fusion energy and begins the longest journey in the cosmos, a trillion-year descent into the gentle embrace of eternal cooling. This is the birth of a white dwarf, a stellar remnant that represents not an ending, but a transformation as graceful as autumn leaves settling into winter's quiet embrace. When we contemplate these cooling stellar cores, we witness the universe's most patient meditation on the nature of time itself, where each passing millennium is but a heartbeat in the cosmic rhythm of cooling and crystallization. The final moments of stellar nuclear fusion unfold like the dying embers of a cosmic campfire that has burned for eons. Deep within the stellar core, where temperatures have raged at tens of millions of degrees, the last hydrogen nuclei find their dance partners in the ancient choreography of fusion. But fuel, even in the vast reservoirs of stellar interiors, is finite. The star's core, having spent billions of years converting hydrogen to helium and helium to carbon and oxygen, finally reaches that threshold where the nuclear fires can no longer sustain themselves against the inexorable pull of gravity. In this moment of transition, the star undergoes its final act of stellar generosity. The outer layers, no longer supported by the outward pressure of nuclear fusion, begin their gentle journey outward, expanding and cooling as they travel. This creates the ethereal beauty of a planetary nebula, gossamer veils of glowing gas that drift away from the stellar core like breath visible on a cold morning. The nebula expands at speeds of tens of kilometers per second. Yet in the cosmic perspective, this expansion unfolds with the unhurried pace of clouds drifting across a summer sky. What remains behind is the stellar core itself, now exposed to the cosmos for the first time in its existence. This core, compressed to extraordinary density by billions of years of gravitational pressure, begins its new existence as a white dwarf. Initially, it glows with temperatures reaching 100,000 to 200,000 Kelvin, radiating with the intensity of 100 suns compressed into a sphere no larger than Earth. Yet this brilliant luminosity marks not the beginning of a new stellar life, but the commencement of the universe's most extended cooling process. The historical discovery of these stellar remnants reads like a cosmic detective story unfolding across decades of careful observation. In 1844, Friedrich Bessel, studying the bright star Sirius with mathematical precision, noticed something extraordinary in its motion across the sky. The star appeared to wobble slightly, as if dancing with an invisible partner. This gravitational waltz suggested the presence of a companion star, yet no such companion could be seen through the telescopes of the time. 18 years later, in 1862, telescope maker Alvan Clark was testing a new 18-inch refractor when he spotted a faint star near Sirius, the elusive companion that had been betraying its presence through gravitational influence. This tiny star, designated Sirius B, appeared unremarkable at first glance, yet it would prove to be one of the most extraordinary objects in the nearby cosmos. When Walter Adams analyzed its spectrum in 1915, he discovered that despite its faintness, Sirius B possessed a surface temperature comparable to that of Sirius itself. The only way this could be possible was if the star were extraordinarily small and dense, a conclusion that challenged the very foundations of stellar physics. From multiple perspectives, the birth of a white dwarf represents a fascinating convergence of physical processes. Through the lens of thermodynamics, we witness a cosmic heat engine finally winding down, its nuclear furnace exhausted, beginning the slow process of radiating away the thermal energy accumulated over billions of years. The laws of thermodynamics dictate that this heat must flow from the hot stellar interior to the cold vacuum of space. But the process unfolds with a patience that makes geological time seem hurried. From a quantum mechanical perspective, the white dwarf represents a triumph of electron degeneracy pressure over gravitational collapse. The electrons in the stellar core, compressed to extraordinary densities, follow the Pauli exclusion principle, which prevents them from occupying the same quantum state. This creates a pressure that has nothing to do with temperature, a quantum mechanical force that holds the stellar remnant in perfect hydrostatic equilibrium. It is as if the very fabric of quantum reality reaches out to cradle these dying stars, preventing their complete gravitational collapse. Gravitationally, the white dwarf achieves a state of exquisite balance. The inward pull of gravity, still formidable, despite the star's reduced mass, finds itself perfectly counterbalanced by the outward pressure of degenerate electrons. This equilibrium will persist for trillions of years, a testament to the fundamental forces that govern our universe. The white dwarf becomes a cosmic meditation on balance itself, demonstrating how opposing forces can create states of perfect, enduring stability. The temporal perspective of white dwarf formation opens windows into deep time that stretch human comprehension. The cooling process that begins with the exposure of the stellar core represents the commencement of a journey that will outlast the current age of the universe by factors of hundreds. These stellar remnants begin their existence glowing with the heat of nuclear fusion's aftermath, but they will spend the vast majority of their existence in states of ever-decreasing temperature, slowly fading from white-hot brilliance to red warmth to infrared glow to eventual darkness. The imagery of these cooling stellar cores evokes the most peaceful metaphors in human experience. Like anvils in cosmic forges that have finally cooled after eons of stellar metalworking, white dwarfs represent the quiet aftermath of stellar creation. They are celestial lighthouses whose beams grow ever dimmer with the passage of time, yet whose light will continue to shine long after our sun has exhausted its own nuclear fuel. These exposed stellar hearts continue to beat with residual heat, their thermal pulse measured not in seconds but in millions of years. The connection between white dwarf formation and the broader tapestry of stellar evolution creates a narrative of cosmic recycling and transformation. The planetary nebula that drifts away from the newly formed white dwarf carries with it the products of stellar nucleosynthesis: carbon, nitrogen, oxygen, and other elements forged in the stellar interior. These elements will eventually become incorporated into new generations of stars and planets, continuing the cosmic cycle of creation and destruction that has operated since the universe's youth. As we contemplate these cooling stellar remnants, we find ourselves drawn into meditation on the nature of endings and beginnings. The white dwarf represents not death in any final sense, but transformation, a change of state as natural and inevitable as water freezing into ice or autumn leaves falling to nourish the soil. In the patient cooling of these stellar cores, we discover a profound lesson about the nature of time itself, where processes that seem eternal from human perspective are merely chapters in the universe's much longer story. In the vast cosmic architecture of space, white dwarf stars stand as monuments to gravitational perfection, their internal structure representing one of nature's most elegant solutions to the eternal struggle between collapse and resistance. These stellar remnants, compressed into dimensions barely larger than our own Earth, yet containing the mass of our Sun, reveal themselves as cosmic cathedrals built from the most exotic materials the universe can create. Deep within these cooling stellar hearts lies a realm where matter exists in states so extraordinary that they challenge our earthbound understanding of physics. The core of a white dwarf, forged from carbon and oxygen atoms created during the star's final nuclear burning phases, exists under pressures so immense that the very electrons surrounding each atomic nucleus have been stripped away and compressed into a sea of quantum mechanical perfection. This degenerate electron gas, as physicists call it with characteristic understatement, provides the structural foundation upon which these stellar monuments rest. The architecture of a white dwarf unfolds like a cosmic Russian doll, each layer revealing new wonders as we journey from the surface toward the crystalline heart. The outermost layer, thin as a whisper compared to the star's radius, consists of hydrogen and helium that could not be shed during the star's final planetary nebula phase. This gossamer envelope, perhaps only a few thousand kilometers thick, glows with residual heat like the last embers of a dying campfire, its light slowly fading across the cosmic night. Beneath this delicate surface layer lies the realm of electron degeneracy, where the fundamental particles of matter have been compressed beyond all familiar scales. Here, electrons move in quantum mechanical lockstep, their behavior governed not by temperature or pressure in any conventional sense, but by the strange laws of quantum statistics. These electrons, packed so tightly that they can barely move, create a pressure that pushes outward against gravity's relentless inward pull, with a force that seems almost miraculous in its precision. The mass-radius relationship of white dwarfs reveals one of the universe's most counterintuitive truths. The more massive a white dwarf becomes, the smaller its radius grows. This inverse relationship, predicted by quantum mechanics and confirmed by countless observations, means that the most massive white dwarfs are also the most compact. A white dwarf containing 60% of our sun's mass might stretch across 8,000 kilometers, while one containing the maximum possible mass of 1.4 solar masses would compress itself into a sphere barely 5,000 kilometers across. This maximum mass, known as the Chandrasekhar limit after the brilliant astrophysicist who first calculated it, represents a fundamental boundary in stellar evolution. Beyond this limit, even the quantum mechanical pressure of degenerate electrons cannot halt gravity's inexorable compression, and the star must find another fate entirely. But for the vast majority of white dwarfs, this limit provides a comfortable margin of safety, allowing them to settle into their eternal cooling phase with the patient dignity of cosmic elders. The internal density of these stellar remnants defies easy comprehension. A teaspoonful of white dwarf material would weigh as much as an automobile, its atoms compressed so tightly that the normal spaces between atomic nuclei have virtually disappeared. Yet this is not the chaotic compression of destruction, but rather the ordered arrangement of matter, finding its most stable configuration under extreme conditions. The electrons, though stripped from their parent atoms, maintain their quantum mechanical properties, creating a pressure that increases with density in precisely the way needed to balance gravity's pull. As we peer deeper into these stellar architectures, we encounter the phenomenon of crystallization, a process that transforms the white dwarf's core from a liquid-like state into a solid crystalline structure over billions of years. This cosmic phase transition begins at the very center of the star, where temperatures and pressures reach their maximum values, and slowly propagates outward like a wave of solidification spreading through the stellar interior. The crystallization process itself represents a triumph of order over chaos as carbon and oxygen nuclei arrange themselves into perfect geometric patterns that would make any crystallographer weep with joy. These structures, primarily body-centered cubic and face-centered cubic arrangements, create a cosmic diamond that spans thousands of kilometers. The formation of these crystalline hearts releases latent heat, much like water releasing heat when it freezes, extending the white dwarf's cooling time by billions of years, and adding another layer of complexity to these already remarkable objects. The surface gravity of a white dwarf creates conditions so extreme that they border on the surreal. Standing on the surface of such a star, if such a thing were possible, would subject you to gravitational forces 100,000 times stronger than those we experience on Earth. The escape velocity from a white dwarf surface approaches 5,000 kilometers per second, a significant fraction of the speed of light itself. This immense gravitational field affects everything from the star's spectrum to the behavior of any material that might fall onto its surface. Historical observations have revealed the remarkable diversity within the white dwarf population. Sirius B, the famous companion to the brightest star in our night sky, serves as the prototype for understanding these objects. Its discovery in 1862 by Alvan Clark marked the beginning of our journey into the realm of stellar remnants. This cosmic lighthouse, orbiting its brilliant companion every 50 years, demonstrates the elegant gravitational dance that can persist for billions of years between a living star and its deceased partner. The contemplation of white dwarf architecture invites us to consider the profound engineering principles that govern cosmic construction. These stars represent the ultimate expression of gravitational architecture, structures so precisely balanced that they can maintain their form for trillions of years without any external support. They are cosmic monuments to the fundamental forces that shape our universe, standing as silent testimony to the elegant mathematical relationships that govern the behavior of matter under extreme conditions. In their patient cooling, white dwarfs embody the gentle persistence of cosmic processes, their internal structure serving as a bridge between the violent nuclear fires of stellar life and the peaceful crystalline order of stellar death. They remind us that even in the most extreme environments the universe can create, there exists a profound order and beauty that speaks to the deepest harmonies of existence. In the profound silence that follows a star's final nuclear heartbeat, a gentle physics begins to govern the cooling remnant that remains. The white dwarf, now freed from the tumultuous pressures of nuclear fusion, settles into a peaceful rhythm of thermal decline that will persist for timescales that dwarf all of human history and stretch toward the very limits of cosmic time itself. The physics of this cooling process unfolds with the patient elegance of a natural law written in the language of thermodynamics and quantum mechanics. Within the white dwarf's compressed heart, heat moves through matter in ways that would seem almost magical to our everyday experience, yet follow principles as fundamental as gravity itself. The stellar remnant becomes a cosmic radiator, slowly releasing the ancient thermal energy accumulated during billions of years of nuclear burning, like a massive stone hearth continuing to warm a room long after the fire has died. The primary mechanism governing this gentle decline follows what physicists call the Debye cooling law, a mathematical poetry that describes how crystalline materials surrender their heat to the cosmos. In the white dwarf's interior, where matter exists in states of compression beyond earthly experience, thermal energy moves through the degenerate electron gas with a conductivity that surpasses the finest metals. This extraordinary efficiency means that temperature differences within the star's interior quickly equalize, creating a nearly uniform thermal profile that cools as a single, coherent entity. During the earliest phases of cooling, when the white dwarf still glows with temperatures exceeding 100,000 degrees, neutrinos play a crucial role in carrying away energy. These ghostly particles, born from the quantum interactions within the dense stellar matter, stream freely through the white dwarf's interior and escape into space at nearly the speed of light. Each neutrino carries away a tiny fraction of the star's thermal energy, contributing to a cooling process that operates on principles of quantum field theory. The neutrino cooling phase represents nature's most efficient cosmic refrigeration system, rapidly drawing heat from the stellar core during the first few million years of the white dwarf's existence. As the white dwarf continues its thermal descent, photon cooling gradually assumes dominance over neutrino losses. The stellar surface, now cooled to temperatures where visible light can escape, begins the long process of radiating away the interior's stored heat. This transition marks a fundamental shift in the cooling physics, as the star transforms from a neutrino-cooled object to a photon-cooled radiator. The surface layers, thin as they are compared to the massive core, act as a thermal blanket that regulates the rate at which interior heat can escape to space. The mathematics governing this cooling process reveals timescales that challenge human comprehension. Leon Mestel's pioneering work in 1952 first quantified these cosmic chronometers, showing that a white dwarf requires approximately 1 billion years to cool from its initial fierce heat to half that temperature. The cooling rate follows a power law that becomes increasingly gentle with time, meaning that each subsequent halving of temperature takes progressively longer. This mathematical relationship ensures that white dwarfs remain detectable for trillions of years, slowly fading through the infrared spectrum like cosmic embers that refuse to be extinguished. Perhaps the most remarkable aspect of white dwarf cooling involves the crystallization process that begins deep within the stellar core. As temperatures drop below approximately 10 million degrees, the carbon and oxygen nuclei that comprise the white dwarf's interior begin to arrange themselves into crystalline structures. This phase transition, occurring under conditions of pressure and density that cannot be replicated in terrestrial laboratories, releases latent heat that temporarily slows the cooling process. The crystallization proceeds gradually from the center outward, creating a solid core surrounded by a fluid mantle, much like the Earth's internal structure, but composed of exotic matter at densities 1,000,000 times greater than water. The release of crystallization energy acts as a cosmic heating system, extending the white dwarf's cooling time by billions of years. This process transforms the stellar interior into something resembling a vast cosmic diamond, with carbon nuclei arranged in crystalline lattices that span thousands of kilometers. The physics of this transformation involves the delicate balance between thermal energy and Coulomb forces, creating conditions where matter transitions from a plasma state to a quantum solid through processes that bridge atomic physics and stellar astrophysics. Throughout this cooling journey, the white dwarf maintains its structural integrity through electron degeneracy pressure, a quantum mechanical phenomenon that prevents further gravitational collapse. The degenerate electrons, compressed into energy states that classical physics cannot describe, provide a pressure that perfectly balances the inward pull of gravity. This quantum mechanical support system operates independently of temperature, ensuring that the white dwarf remains stable even as it cools toward absolute zero over cosmic time. The thermal conductivity of degenerate matter facilitates this cooling process with remarkable efficiency. Heat moves through the white dwarf's interior via electron conduction, much like heat flowing through a metal rod, but with conductivities that exceed terrestrial materials by factors of thousands. This extraordinary heat transport ensures that the white dwarf cools uniformly, maintaining thermal equilibrium throughout its interior while slowly radiating energy from its surface into the cosmic void. As we contemplate these gentle physics of stellar cooling, we encounter a profound meditation on the nature of time itself. The white dwarf's cooling curve represents one of the universe's most patient processes, unfolding over timescales that span from the current cosmic age to epochs trillions of years in the future. Each photon escaping from the white dwarf's surface carries away a quantum of ancient stellar energy, contributing to a cooling process that will continue long after our sun has exhausted its nuclear fuel and joined the ranks of these slowly fading stellar remnants. In the vast theater of cosmic time, where moments stretch into millennia and millennia dissolve into eons, white dwarf stars embark upon their most profound journey, a cooling odyssey that unfolds across time scales so immense they challenge our very conception of permanence. These stellar remnants, having shed their outer layers in gentle planetary nebulae, now begin their trillion-year meditation on the nature of time itself, cooling with a patience that speaks to the deepest rhythms of the universe. The cooling of a white dwarf unfolds in distinct phases, each characterized by its own serene beauty and profound temporal significance. In the initial phase, lasting perhaps 1 billion years, a time span that encompasses the entire history of complex life on Earth, these stellar remnants shine with temperatures exceeding 100,000 Kelvin, their surfaces blazing with blue-white radiance that gradually, imperceptibly, begins to fade. Like cosmic lighthouses slowly dimming their beacons, they enter what astronomers call the hot white dwarf phase, where their surfaces still glow with the fierce heat of their stellar past. During these early cooling centuries, the white dwarf's internal structure undergoes profound transformations. The degenerate electron gas that supports the star against gravitational collapse conducts heat with remarkable efficiency, creating thermal currents that flow through the stellar interior like slow rivers of energy. Neutrinos, those ghostly particles that interact so weakly with matter, carry away vast quantities of energy in the star's youth, accelerating the initial cooling process. These invisible messengers of stellar death stream outward at the speed of light, carrying with them the thermal legacy of nuclear fusion that once powered the star's luminous life. As millions of years pass, time frames that dwarf human civilization yet represent mere moments in the white dwarf's cooling journey. The star's surface temperature gradually decreases. The transition from blue-white to white to yellow occurs over timescales that make geological processes seem hurried. The star's spectrum shifts toward longer wavelengths, its peak emission moving from the ultraviolet through the visible spectrum toward the infrared, like a cosmic sunset that unfolds over billions of years. The second phase of cooling, spanning the next 10 billion years, represents the warm white dwarf era. During this extended period, the star's surface temperature drops from tens of thousands of degrees to perhaps 5,000 Kelvin, roughly the temperature of our sun's surface. Yet this seemingly modest temperature decrease occurs over a time span twice as long as the current age of the universe. The star's luminosity fades by factors of thousands, its gentle radiance becoming increasingly difficult to detect across the cosmic distances that separate us from these ancient stellar corpses. Throughout this warm phase, the white dwarf's interior continues its slow transformation. The carbon and oxygen nuclei that comprise the star's core begin to arrange themselves into crystalline structures, forming what astronomers poetically describe as stellar diamonds. This crystallization process releases latent heat, temporarily slowing the cooling rate and extending the star's visible lifetime. The formation of these cosmic crystals occurs over millions of years as the stellar interior transitions from a fluid plasma to a solid, crystalline lattice that spans the entire volume of the cooling star. The third cooling phase extends across the following 100 billion years, as the white dwarf transitions into what we might call the cool phase. During this vast epoch, the star's surface temperature drops to perhaps 3000 Kelvin, and its color shifts from yellow through orange to deep red. The star's luminosity decreases to mere thousandths of its initial brightness, making it increasingly difficult to observe even with our most sensitive instruments. Yet the star continues its patient cooling, radiating its stored thermal energy into the cosmic void with unwavering determination. In this cool phase, the white dwarf's crystalline core reaches full solidification, becoming a cosmic jewel of compressed carbon and oxygen that spans thousands of kilometers. The star's surface layers, thin shells of hydrogen and helium inherited from its stellar past, continue to conduct heat outward, though at increasingly slower rates. The thermal timescales become so extended that the star's temperature changes are imperceptible across human lifetimes, civilizations, and even species. The final phase of white dwarf cooling stretches across trillions of years, timescales so vast they encompass the entire future evolution of the universe as we know it. During this ultimate epoch, the star's surface temperature drops below 1000 Kelvin, and its emission shifts entirely into the infrared spectrum. The star becomes what astronomers call a black dwarf, though this transition occurs so far in the future that no black dwarfs yet exist in our 13.8 billion-year-old universe. These theoretical objects would be invisible to optical telescopes, detectable only by their gravitational effects and the faint infrared radiation they continue to emit. Throughout this trillion-year cooling journey, the white dwarf serves as a cosmic timekeeper, its temperature and luminosity providing precise measurements of the time elapsed since its formation. Astronomers use these stellar chronometers to study the history of star formation in our galaxy, determining the ages of stellar populations and constraining models of galactic evolution. The oldest white dwarfs in our galaxy, with cooling ages approaching 10 billion years, represent some of the earliest stars to complete their nuclear burning phases and transition to this final stellar state. The cooling curves of white dwarfs reveal the profound patience inherent in cosmic processes. Unlike the dramatic explosions of supernovae or the violent accretion events around black holes, white dwarf cooling represents the universe's capacity for gentle, sustained transformation. These stars cool with the same unhurried pace that governs the erosion of mountains, the drift of continents, and the slow dance of galaxies through cosmic space. They remind us that the universe operates on timescales that transcend human experience, yet follow physical laws we can understand and appreciate. In contemplating the trillion-year cooling of white dwarf stars, we encounter a profound meditation on the nature of time itself, finding in these ancient stellar remnants a peaceful wisdom that speaks to the deepest rhythms of cosmic existence. In the deepest interiors of these cooling stellar remnants, a transformation of breathtaking beauty unfolds across timescales that stretch human imagination to its very limits. Within the compressed hearts of white dwarf stars, where matter exists in states impossible anywhere on Earth, the ancient carbon and oxygen nuclei begin their slow, inevitable journey toward perfect crystalline order. This is perhaps the most serene and meditative process in all of stellar evolution, a gentle transition from the chaotic thermal motion of stellar fire to the perfect geometric harmony of crystalline structure. The crystallization of a white dwarf's core represents one of nature's most patient architectural projects. Deep within these stellar remnants, where temperatures still hover at millions of degrees and pressures exceed anything imaginable in terrestrial experience, carbon and oxygen nuclei move in their ancient dance of thermal motion. Yet as the millennia pass and the star continues its relentless cooling, these nuclei begin to sense each other's presence more strongly. The thermal energy that once kept them in constant chaotic motion gradually diminishes, allowing the fundamental forces of electromagnetic attraction to assert their organizing influence. This transformation begins at the very center of the white dwarf, where the density reaches its maximum and the cooling proceeds most rapidly. Here, in a sphere perhaps only a few hundred kilometers across, the carbon and oxygen nuclei first begin to arrange themselves into the perfect geometric patterns that will eventually characterize the entire stellar core. The process resembles the formation of ice crystals in a winter pond, but played out across cosmic timescales and under conditions of such extreme density that a teaspoon of this crystallizing matter would weigh as much as an automobile. The crystalline structures that form within these stellar hearts are marvels of natural engineering. The carbon and oxygen nuclei, stripped of their electrons by the intense pressures, arrange themselves into body-centered cubic lattices of stunning regularity. Each nucleus finds its place in this three-dimensional chess game of atomic architecture, creating structures that extend throughout the stellar interior with a precision that would make human engineers weep with envy. These are not the random, imperfect crystals we might find in earthly minerals, but perfect geometric forms that span thousands of kilometers, created by the patient work of gravitational compression and thermal cooling. The famous white dwarf, BPM 37093, affectionately known as the Diamond Star, offers us a window into this crystalline transformation. Located some 50 light-years from Earth, in the constellation Centaurus, this ancient stellar remnant has cooled sufficiently for its core to undergo extensive crystallization. The carbon nuclei within its heart have arranged themselves into structures remarkably similar to diamond, though under conditions of temperature and pressure that make terrestrial diamond formation seem gentle by comparison. This cosmic jewel, with a mass comparable to our Sun, compressed into a volume smaller than Earth, represents the ultimate expression of stellar crystallization. As the crystallization process advances through the white dwarf's interior, it releases latent heat in much the same way that water releases heat when it freezes into ice. This additional energy source significantly extends the cooling timescales, adding billions of years to the star's thermal evolution. The process is so gradual, so patient, that the crystallization front advances through the stellar interior at a pace measured in geological ages. What begins as a small crystalline seed at the star's center slowly grows outward, like frost patterns spreading across a cosmic window pane, until eventually the entire core achieves perfect crystalline order. The seismic properties of these crystallizing white dwarfs provide astronomers with remarkable insights into their internal structure. Just as earthquakes reveal the layered structure of our planet's interior, stellar quakes in white dwarf stars create oscillations that penetrate deep into their crystalline hearts. These cosmic seismometers allow us to map the progress of crystallization, revealing the boundaries between liquid and solid regions with extraordinary precision. The pulsating white dwarf stars, with their regular brightness variations, serve as natural laboratories for studying the physics of matter under extreme conditions. The timescales involved in this crystallization process speak to the profound patience of cosmic evolution. A white dwarf star may require several billion years to cool sufficiently for crystallization to begin, and then many billions more for the process to reach completion. During this vast span of time, entire galaxies evolve, stellar populations rise and fall, and the universe itself expands and cools. Yet through it all, these stellar remnants continue their slow, methodical transformation from chaotic thermal motion to perfect crystalline order, marking time with the patience of geological ages. The crystalline hearts of white dwarf stars represent more than mere curiosities of stellar physics. They are cosmic monuments to the fundamental organizing principles of nature. In their perfect geometric structures, we see the same forces that create snowflakes and mineral crystals, but operating under conditions of such extremity that they stretch our understanding of matter itself. These stellar diamonds, formed in the hearts of dying stars, remind us that even in death, the universe continues to create structures of breathtaking beauty and mathematical perfection, waiting patiently across the vast expanses of cosmic time for their moment of crystalline transformation. In the vast cathedral of space, where silence reigns eternal and time moves with the patience of geological epochs, astronomers have learned to read the gentle stories written in starlight across billions of years. These stellar fossils, the white dwarf remnants scattered throughout our galaxy, like ancient pearls on cosmic velvet, serve as observational windows into the deepest reaches of time itself. Each cooling ember carries within its fading glow the accumulated wisdom of stellar evolution, waiting patiently for our telescopes to decipher their quiet testimonies. The art of studying these distant lighthouses requires instruments of extraordinary precision and sensitivity. The Hubble Space Telescope, floating serenely above Earth's atmospheric veil, has spent decades capturing the subtle hues of cooling white dwarfs, creating color magnitude diagrams that reveal the gentle progression from blue-white heat to red-orange warmth. These stellar portraits, accumulated over years of patient observation, form cooling sequences that trace the unhurried journey from nuclear fire to crystalline silence. Each data point represents not merely a measurement, but a moment frozen in the trillion-year cooling process, a snapshot of stellar evolution unfolding across cosmic time. The European Space Agency's Gaia mission has revolutionized our understanding of these stellar remnants through its meticulous parallax measurements, determining distances with unprecedented accuracy. Like a cosmic surveyor, Gaia maps the three-dimensional positions of white dwarfs throughout our galactic neighborhood, revealing their gentle motions through space with precision, measured in milliseconds. These tiny angular shifts, detected across years of observation, unlock the fundamental parameters needed to understand each star's cooling history. The spacecraft's patient vigil, measuring stellar positions with the precision of a master clockmaker, transforms subtle changes in apparent brightness into absolute luminosities, revealing the true nature of these cooling stellar hearts. Ground-based observatories contribute their own gentle revelations through spectroscopic analysis, dispersing white dwarf light into rainbow spectra that tell stories of surface composition and temperature. The absorption lines etched into these stellar signatures reveal whether hydrogen or helium dominates the thin atmospheric layers, while the overall spectral shape whispers of surface temperatures that have been declining for billions of years. These spectroscopic fingerprints, captured through long exposures under dark skies, provide the detailed atmospheric parameters needed to model the cooling process with scientific precision. The process of studying white dwarf cooling sequences resembles archaeological excavation conducted on cosmic scales. Astronomers carefully catalogue each stellar remnant, measuring its brightness across multiple wavelengths of light, from ultraviolet through infrared. These multicolor observations reveal the gentle temperature gradients that characterize different stages of cooling, creating a stellar census that spans the full range from recently formed blazing hot white dwarfs to ancient cool specimens that have been fading for most of the universe's current age. Each measurement adds another piece to the vast puzzle of galactic evolution. Proper motion studies reveal the kinematic signatures of white dwarf populations, their gentle movements through space, encoding information about their origins and ages. The fastest-moving white dwarfs often belong to the galaxy's ancient halo population, their high velocities reflecting the turbulent conditions of early galactic formation. These stellar wanderers, discovered through patient surveys comparing photographic plates separated by decades, carry within their motion the memory of the galaxy's youth, when star formation proceeded at a more vigorous pace and stellar populations were still sorting themselves into the organized structure we observe today. The statistical analysis of white dwarf populations provides profound insights into the history of star formation in our galaxy. By counting the numbers of white dwarfs at different cooling stages, astronomers can reconstruct the rate at which stars have been dying over cosmic time, creating a stellar death certificate that extends back billions of years. These population studies reveal the gentle ebb and flow of stellar birth and death, showing how the galaxy's stellar generations have succeeded one another in the slow dance of cosmic evolution. Modern large-scale surveys, such as the Sloan Digital Sky Survey, have catalogued thousands of white dwarfs, creating vast databases that enable statistical studies of cooling processes. These comprehensive censuses reveal the subtle variations in cooling rates caused by different stellar masses, compositions, and evolutionary histories. The accumulated data forms a stellar library that spans the full range of white dwarf properties, from the most massive specimens approaching the Chandrasekhar limit to the least massive products of the lowest mass main sequence stars. The gentle precision required for these observations reflects the patient nature of the cooling process itself. White dwarfs change so slowly that their evolution can only be detected through the accumulated observations of many individual stars at different cooling stages. Like studying the growth of ancient trees, by examining specimens of different ages, astronomers piece together the cooling sequence by observing the full population of stellar remnants, each one representing a different moment in the trillion-year journey from stellar death to cosmic silence. In the vast tapestry of cosmic time, white dwarf stars serve as nature's most patient and reliable chronometers, their cooling curves marking the passage of billions upon billions of years with extraordinary precision. These stellar remnants, scattered throughout our galaxy like ancient timepieces, offer astronomers a unique window into the deep history of the universe, their gentle cooling providing a cosmic calendar that spans epochs far beyond human comprehension. The principle underlying white dwarf chronometry rests in the beautiful simplicity of their cooling process. Unlike the complex nuclear reactions that power living stars, white dwarfs follow predictable thermodynamic laws as they slowly radiate away their stored thermal energy. This cooling occurs with such regularity that astronomers can work backward from a white dwarf's current temperature to determine precisely when it first began its long journey toward darkness. The mathematics of this process reveals itself in cooling curves that stretch across cosmic time like gentle, descending melodies. Consider the ancient white dwarfs discovered in globular clusters, those magnificent stellar cities that orbit our galaxy's halo like distant satellites. These clusters, among the oldest structures in the universe, contain white dwarfs that have been cooling for more than 12 billion years. Their faint luminosity speaks of temperatures that have dropped to mere thousands of degrees, down from the hundreds of thousands of degrees they possessed when they first emerged from their planetary nebula cocoons. Each degree of cooling represents millions of years of patient thermal evolution, a testament to the unhurried pace of cosmic processes. The study of these cosmic chronometers has revealed fascinating insights into galactic archaeology. White dwarfs in the galactic disk tell stories of more recent star formation, their relatively higher temperatures indicating ages of several billion years. In contrast, the rare white dwarfs found in the galactic halo, those ancient wanderers that trace vast elliptical orbits around our galaxy's center, reveal cooling ages that approach the age of the universe itself. These stellar fossils preserve within their crystalline cores the chemical signatures of the earliest generations of stars, making them invaluable records of cosmic chemical evolution. The initial-final mass relationship provides another layer of chronological information, connecting the mass of a white dwarf to the mass of its progenitor star. More massive progenitor stars lived faster, more intense lives, reaching the white dwarf stage more quickly than their lower mass cousins. By studying the masses of white dwarfs in stellar populations of known age, astronomers can reconstruct the star formation history of our galaxy, tracing how the rate of stellar birth has changed over cosmic time. In the solar neighborhood, detailed studies of nearby white dwarfs have revealed the complex structure of our local galactic environment. The kinematics of these stellar remnants, their motions through space, tells stories of galactic dynamics spanning billions of years. Some white dwarfs move in the orderly rotation of the galactic disk, while others follow more chaotic paths that speak of ancient gravitational encounters or origins in disrupted stellar systems. The precision of white dwarf chronometry continues to improve with advancing observational techniques. Space-based telescopes, freed from the blurring effects of Earth's atmosphere, can measure the faint light of cool white dwarfs with unprecedented accuracy. Spectroscopic studies reveal not only their surface temperatures, but also their atmospheric compositions, providing clues about the nuclear processes that occurred in their progenitor stars billions of years ago. These cosmic timepieces also serve as laboratories for testing our understanding of fundamental physics. The cooling rates of white dwarfs depend on exotic processes, such as neutrino emission and crystallization in degenerate matter, phenomena that cannot be replicated in terrestrial laboratories. Observations of white dwarf cooling sequences thus provide unique tests of theoretical physics in extreme conditions. As we peer deeper into space and further back in time, white dwarfs offer glimpses of the universe's earliest epochs. The coolest, faintest white dwarfs represent the oldest stellar remnants we can observe, their ancient light carrying information about conditions in the young universe when the first generations of stars were forming and dying. These stellar archaeologists continue their patient cooling, marking time with the steady rhythm of thermal radiation. Each photon they emit a gentle reminder of the vast scales on which cosmic processes unfold. In contemplating these cosmic chronometers, we find ourselves connected to the deepest rhythms of the universe, where time is measured not in heartbeats or seasons, but in the slow, steady cooling of stellar remnants across trillions of years. The eternal lullaby of cooling stars as we reach the gentle end of our journey through the trillion-year silence of white dwarf cooling. We find ourselves wrapped in the profound peace that comes from understanding cosmic time itself. These stellar remnants, these ancient hearts of long-dead stars, offer us perhaps the most serene meditation on the nature of endings that the universe provides. Throughout our exploration, we have witnessed the extraordinary patience of cosmic processes, the slow, inevitable cooling that transforms blazing stellar cores into crystalline jewels floating in the cosmic dark. We have seen how white dwarfs, these Earth-sized remnants of solar mass stars, begin their trillion-year journey from temperatures exceeding 100,000 Kelvin to the eventual cold silence of black dwarfs, marking time on scales that dwarf all human experience. The beauty lies not in dramatic stellar explosions or violent cosmic collisions, but in the gentle, unhurried process of cooling itself. Like cosmic campfires slowly banking their ancient flames, these stellar remnants teach us about the profound tranquility found in gradual transformation. Their crystallizing cores, forming diamond-like structures over billions of years, remind us that even in death, stars create beauty of incomprehensible delicacy. As we contemplate these cooling stellar hearts, we discover a deep comfort in their patient journey. They are not racing toward oblivion, but moving with the measured pace of cosmic time, each millennium bringing only the slightest dimming of their ancient glow. This is the universe's own meditation on impermanence, not rushed or anxious, but flowing with the natural rhythm of thermodynamic inevitability. The white dwarfs we have studied tonight, from Sirius B, the first discovered, to the countless others scattered throughout our galaxy, serve as gentle reminders of our place in the vast cosmic story. They are witnesses to stellar generations that lived and died billions of years before our sun was born, and they will continue their slow cooling long after our own star has joined their silent ranks. In their trillion-year journey from stellar fire to cosmic ice, these remnants embody the ultimate peace that comes from accepting the natural flow of time. They do not struggle against their fate, but embrace it with the dignity of celestial bodies that have already given their all, having fused hydrogen into helium for billions of years, creating the heavy elements that make planets and life possible. Let your mind now drift with these cooling stars, feeling the vast timescales that govern their gentle transformation. Imagine floating peacefully among these ancient stellar hearts, each one a glowing ember in the cosmic fireplace, slowly releasing the last of their nuclear warmth into the infinite night. Feel the profound silence that surrounds them, not empty or lonely, but full of the patient wisdom that comes from having witnessed the birth and death of stellar generations. As you settle into sleep, carry with you the serene knowledge that somewhere in the galaxy, countless white dwarfs are continuing their slow, peaceful cooling, marking cosmic time with their gentle dimming. Their trillion-year lullaby plays on frequencies beyond human hearing, a cosmic meditation on the beauty of gradual transformation, the peace found in accepting the natural flow of time, and the profound comfort that comes from understanding our place in the vast, patient universe. Let their ancient light, slowly fading across the eons, guide you into the deepest, most peaceful sleep, where time moves with the gentle rhythm of cooling stars, and consciousness dissolves into the same cosmic tranquility that governs these stellar remnants on their billion-year journey toward the ultimate silence of space.